also I will do a little bit additional. Yeah, the one last time we went over is a little bit too quick, and then we give it a try again. So this time I will try to make a better symbol. So basically here, this one, we consider one elastic beam and under any some kind of loading. So for example, if we choose the loading applied at the free end here, and we choose the degree of freedom and with the displacement of the free end. So let me choose the zeta. Okay, that is the symbol for degree of freedom. Okay, so zeta denoting is the degree of freedom, so that means indicating is the distance here. Okay, so that is our degree of freedom. So we try to describe the equivalent spring constant and then equivalent mass. And for this case, so basically here we want to find is the MEQ and also KEQ with respect to the degree of freedom zeta. Okay, so here I use the symbol eta for describing. And also in addition, and let me assign the coordinate systems because here I want to have a proper description for the deflections. So let me assign this is the x. Okay, so horizontal axis direction, this is x. So in particular, let me pick this element here. Okay, this small element, it has the small length, let me call it dx. So basically this element is measuring from this end to here is x. Okay? And for that particular element, and we take, so basically here the displacement at this point and from mechanical material, so let me call this is called the y-axis. Okay, so that is the deflection y, and as a function of the position. And for x equal to 0, then that is the clamp site and 0 deflection. When x equal to L, the whole length, then the deflection equal to our degree of freedom. Again, the degree of freedom is a parameter depends on the magnitude of the loading. Once the loading is determined, then this value eta is determined. So basically here I would say this is the parameter depends on how big the magnitude of the loading we apply. Okay. So from using those notations, then we can write is from mechanics material from I would say from mechanics material ES331, and we have such a formula we can provide is this. And so y-axis can be related to eta. So for example, the eta is the diffractions at the free end. And that one from mechanical material we can describe it as PL3 and 3EI. Okay, and again that is depends on the geometry, material properties, and in particular is a function of the loadings. And also the diffraction at any point we can describe as the function of the eta, and that one we can be equal to this one and x squared and 3L minus x and times theta. Okay, so you simply plug in the data to here, you can directly calculate y of x, and given the material properties, given the magnitude of the loading. So therefore, from here, if we consider that is a function of time, for example, say if this everything changing is a function of time, so that means let the degree of freedom is a function of time. So importantly, we can calculate velocity at this small element, that is 2L3 x squared 3L minus x and times theta dot. Okay, so the displacement of the beam in terms of function, we simply take the dot on the two parameters, because for this term here, everything is time independent. So if we take the, say, the time derivative, then we know right away only apply to this term. This is a little bit additional new information beyond the ES331. And we're going to use this information. So right now, the first one to determine the equivalent mass, and we can try is this. We formulate the kinetic energy of this continuum system. So kinetic energy, and will be equal to, we consider the small element, the dx. So so let me assume the rho is the density of the mass per unit length. So basically here the rho times dx is representing the small mass of this element, okay, dx, and multiply is corresponding velocity square. So mass multiply velocity square divided by q. That is the energy, kinetic energy of this small element. And we do the integrations, which means we take the summation of such energy from individual elements, and integrating is x is from 0 to L. So this representing is the entire kinetic energy of this flexible beam once it's under vibrations. Okay. So once we have this one, we simply plug in y dot to here, and so let me rearrange. And so if you implement this one, basically here you can see the y dot is a function of x, and you simply do a little bit more kind of a few more minutes to explain the square of these terms, and then do a little bit more, then skip up the whole thing. Eventually, we will lead into this term, 33 times rho L, and 140 times zeta dot square. Okay. On the other side, for these equivalent systems, and for these equivalent systems, we have the kinetic energy equal to, we want to get is the equivalent mass, and representing the equivalent mass in terms of the degree of freedoms. The degree of freedom has a velocity eta dot and square. So that is from the equivalent description of the system. So you compare to here, so basically this term is equal to MEQ. Is this one. Okay. And now we solve for the KEQ. So the KEQ is pretty straightforward. So the KEQ is such that, again, let me write it up here. So this is the P, and this is the diffractions, and this is our degree of freedoms, eta, and eta is P L3 3EI. And this one is equivalent to a string, KEQ. And this one has the degree of freedom eta measured from here. So from here you can see basically force divided by displacement. That by definition is our KEQ. Okay, from this one. And also with the range from this equation, can you see again P over zeta equal to 3EI divided by LQ. Are we good? So from here we have the MEQ, we also have the KEQ, and then I will keep this for a little bit more, and then we will talk about the natural frequencies here. So that is the illustrations of a little bit more the rigorous examples to demonstrate, the kind of summarize what we have learned for equivalent mass and for equivalent spring constant. So Dr. Harvard, we can stop here.